In this lesson, we will be looking at permutations, combinations, and the binomial theorem. In this lesson, we're going to talk more about the properties of combinations and some more applications.
Okay, this section we're going to be looking at some restrictions on combinations in much the same way that we did with permutations here. The thing to notice here, one of the key ideas is something that we've hinted at before in a previous lesson here, that if you've got n objects and you're choosing r of them, actually maybe we should zoom in on this. If you choose r of them, you can get the same result by choosing n minus r of them. Okay, and the way you think about this, for example, is let's say you've got, let's say you've got 5 objects and you're choosing 2 of them. Let's say that there's, let's say, 5 different candy bars on the shelf and I'm choosing 2 of them. Choosing 2 bars to take gives exactly the same result as choosing 3 bars to leave behind. These are identical. As long as these 2 values right here have a sum equivalent to the first number here, the 2 combinations will be the same. Okay? So anyway, that in itself isn't a good reason for this. We'll show you, I'll give you a bit of a demonstration in just a few moments as to algebraically why this would hold. But I hope conceptually the idea makes sense. Okay? So you've got 1, 2, 3, 4, 5. Me taking these, okay, is the same as choosing to ignore those. It's the same result. A couple other things you want to note here. N choose 1 is just n. It makes perfect sense. How many ways can you choose one object, let's say from a group of 10? Well, there's 10 ways of doing it, okay? How many ways can you choose 10 objects from 10 objects? Well, there's only one way to do that. You choose all of them. You just grab them, okay? And then lastly here, how many ways, and this maybe is a little bit of a weird one conceptually here, but n choose 0. How many ways can you look at a group of 10 objects and do nothing? Just the one way, by doing nothing, okay? And so n choose 0 is going to be equal to 1. Again, it's kind of a weird one to get your head wrapped around, but yeah, n choose 0 is just going to be equal to 1.
Show algebraically why 10 choose 2 is equal to 10 choose 8.
Okay, so hopefully after we've illustrated why this works here, why 10 choose 2 is the same as 10 choose 8, you'll get a better appreciation as to the relationship there in a more general sense. So first of all, 10 choose 2. If I write this using the factorials here, I will get 10 factorial divided by, that's going to be the left side minus the right side. So 10 minus 2 factorial, and then right side factorial. So left side factorial over left side minus right side factorial, right side factorial. Now, I'm just going to do a little bit of simplification here. 10 minus 2 is 8. So this is going to be 10 factorial over 8 factorial, 2 factorial. Okay? Now, here's where, this is where, where math, I don't know, I like this. I like what we do here. Okay? 2 actually can be rewritten. Okay, I could totally rewrite that as, okay, there's my 8 factorial. I could rewrite 2 as 10 minus 8. I mean, I've done nothing. I have really done nothing. 10 minus 8 is 2. Those are one and the same. However, look what that does for me. Now, if you're not seeing it right here, what I'll do here is I'll take advantage of the fact that this is 8 factorial multiplied by 10 minus 8 factorial. They're multiplied together. Order does not matter for multiplication, so this is like 10 minus 8 factorial, 8 factorial. And that is now exactly in the form that I need it to be for me to interpret this as 10 choose 8. Okay? All along the way here, every one of these steps is identical to the one in front of it. They're completely equal. And so our result here is that 10 choose 2 must be identical to 10 choose 8. Choosing to take 2 objects from a group of 10 is exactly the same as choosing to ignore 8 objects from a group of 10.
A committee of 5 is to be formed from 7 females and 6 males. Find the number of committees possible if they must have exactly 3 females.
Okay, so in this case here, We're back to committees. We're going to create a committee of 5, and we're choosing from 7 females and 6 males here. So, but our restriction here is exactly 3 females. Exactly 3 females. Now, the implication here, although it's not stated, is that if you've got 3 females, you must therefore have 2 males, because I need to have a committee of 5. So how do I get 3 females? Well, that's going to be 7, choose 3 of them, and then because I need females and males, I would do 6, choose 2. Okay, now when I enter that in my calculator, and I've shown you that before, how you go about doing that, pressing the math button, going to the probability menu. So when you do that, you will get 525 different committees that have exactly 3 females on it.
At least one female.
Okay, to do this at least one female question, there are 2 very distinct ways you could do this, and although one of them is a little bit longer than the other, I think for a lot of people it just makes more sense. Okay, at least one female means you could have 1 or more females here, right? So let's talk about this. How many ways could you choose a female? Well, you've got 7, you could choose 1. But if you've got 1 female, you have to have 4 males. So that would be 1 female and 4 males. Or you could do 7, choose 2, because you could have 2 females and 3 males. Okay? Or you could have 7, choose 3 females and 2 males. Or you could have 7, choose 4 females and 1 male. Or you could have 7, choose 5 females, and you could choose none of the males. Now, I don't really need this 6, choose 0. It's just going to be equal to 1. But it's a kind of a placeholder. So you notice here that I'm still choosing from 13 people, and I'm still choosing 5. Okay? So that's kind of consistent all the way through here. 13 people choosing 5, 13 people choosing 5, and so on. This is longer than the other method I'm going to show you, but it makes sense. I can see every step along the way exactly how this committee is being constructed. But this is equal to, there is another way of doing this. The other way of going about doing this is to just look at the fact that I've got 13 people. Like, don't worry right now about male or female. There are 13 people, and I need to choose 5. 13 choose 5 is the total number of ways I can choose a committee here without restrictions. Okay? Now, I want at least 1 female. But what's the exact opposite of at least 1 female? Well, think about that. At least 1 female means I could have 1 female, 2, 3, 4, 5. So the exact opposite would be, well, none of them. No females in the committee. So that's what I do. 13 choose 5, and then I'm going to subtract from all of the possible committees. I'm going to subtract the ones that I don't want. The ones I don't want are all the committees that don't have females on them. And if they don't have females, there's 7 choose 0. There's no females. They are all male. Okay? So all of the committees minus the ones with no females. Now, the results are going to be exactly the same. This is just a whole lot quicker to type into the calculator. And the answer here is 1,281 different committees that have at least 1 female on them.
At most 3 males.
Right, at most 3 males. Now that means you could have no males, 1 male, 2 males, or 3 males. Okay, that's kind of how we're building this one here. So in this case right here, let's just build this from scratch here. We could have all females. So in other words, 7 choose 5 and no males. Okay, because at most 3 means up to 3. Or we could choose and have 4 females, and there could be just 1 male. Or we could choose 3 females, in which case we'd need to have 2 males, or 2 females, and there's our 3. There's our 3 males right there, and there's the maximum there. So this could happen in, what do we got here, 4 different ways. Now, we could do this another way, okay? We could do this another way. We could, just like in the previous question, we could take a look at all the possible committees and then subtract from them the ones that we don't want here. And if it's at most 3 males, then what we're doing is we're going to get rid of the ones that have more than 3 males. So, and there are two ways that that could happen. So you could have, for example, just 1 female and 4 males, or we could get rid of the one where that had no females, and what do we have there? All 5 males. Okay? And so now, when we enter that in, and I'm just going to go to my calculator really quickly here because I haven't done this one quite yet. This will be math probability, choose. And in this case here, we're going to get 1,176 different committees that have at most 3 males.
At least 3 females.
Okay, before we leave this question entirely, I wanted to throw my own question in here. What if we do at least 3 females? Okay, the reason I want to go through this question is because it showed up on an assignment that I gave to students a few years ago, and there was a misunderstanding. Somebody out there had a really neat idea as to maybe a shortcut for doing a question like this. And then this person shared it with their friends, and they all got it wrong on the exam. That idea kind of went away, and then it resurfaced a little while later. Somebody else had this quote-unquote brilliant idea, and I want to address this and make sure that nobody misunderstands what's going on here. At least 3 females. Let me show you first of all the correct way to do this. Okay, at least 3 females means you could have, from the 7 females, you could choose 3. And that means you'd have to choose 2 males, or you could choose 4 females, in which case you're only choosing 1 male, or you could choose all 5 females and you don't choose a male. So here we go: 3 women, 4 women, 5 women, and when you evaluate that, you get 756. Now, the other way of doing this that is still correct would be to take, again, 13 choose 5, all of the different committees here, and then subtract the ones that have less than that. So you would subtract the no women, minus 1 woman, minus 2 women. Now, I don't want to necessarily write that all out right now. I'll deal with that in a second here. But this would also work here. Here was the incorrect idea, and there was a certain logic to it. And this is why I want to address this, because I don't want you to inadvertently stumble across, hey, a great idea, only for it to be very, very wrong here. This is how their logic worked. They took and chose 3 women. Then what they did is they took the remaining 4 women that they didn't choose and threw them back into the group with the men. So if you add those 4 women to the group of men, you have 10 people now to choose from, and you're going to choose 2 more. Now think about this. This means you've chosen 3 women, so you know for sure that whatever committee you create is going to have at least 3 women in it. And then you're going to choose from a group. Now you might choose another woman and a man. You might choose 2 more women, or you might just choose 2 men. Either way, you're going to have at least 3 women, and that has a certain logic to it. But the problem is that this particular result here, the answer is 1575. It is substantially larger than the number that we're looking for. Okay, and that's because this particular method here actually doubles up on solutions. It counts the same group of people twice here. So think about it like this. You've got, let's say you've got, we had 7 females to choose from. You could have done it like this. Let's say you chose woman A, B, C, and then you chose, in your 7 choose 3, and then in your 10 choose 2, you chose woman D and man Z. Okay? But you could have done this slightly differently. You could have chose women A, B, D. Okay, and then when you put those other women back in there, chosen woman C and then man Z. And so, like, notice these two committees are exactly the same, Okay, but they're counted differently because this 7 choose 3 is different than this 7 choose 3. And these are different as well. So this particular method treats these as different, and that's why this number is substantially larger. This is not the way to do this. So please, 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 when you see something like this, at least 3 females, and this number is kind of midway in the group there. Okay, we were choosing a group of 5. Okay, when you do something like this, build it from scratch. Build it piece by piece. You'll be much happier with your result at the end.
How many ways can a committee of 2 girls and 3 boys be selected from a group of 6 girls and 8 boys if Jack and Jill cannot both be on the same committee?
Okay, this is kind of an interesting little scenario here. We're going to have 2 girls and 3 boys on the committee here. We got 6 girls and 8 boys to choose from, but we can't have Jack and Jill together. You know, I don't know what they're in love, and when you get them together, they can't focus on anything. So you can't have those 2 together here. So there's a couple of different ways we can do this. First of all, you could have one of them on the committee. Okay? So let's say, for example, that we had Jack on the committee, but not Jill. Okay, so we had Jack, but not Jill here. Now, that means we've still got 2 other boys to pick. Now, there's still 7 boys to choose from, and so we got to pick 2 of those boys. And we've still got 5 girls to choose from, and we need to choose 2 girls here. So looking at the group here, we've got 1, 2, 7 is 9, and 5 is, what we got to, sorry, I lost track of my own little addition there. 1, 2, 9, 14. Okay? And then we're choosing 1, and there's our 5, 2 and 2. There's our 5 group. So that's exactly correct there. Or, because this isn't the only way this could have happened here, or instead of choosing Jack, we chose Jill. Okay? In which case, we would need to choose 3 boys, but now from the 5 remaining girls we only need to choose 1 because we already have 1. So this could happen either one of these 2 ways here. Or, okay, and this is an important one here. We told you that Jack and Jill cannot both be on the committee. But what we've done here is we have Jack on the committee, here we have Jill on the committee, but don't assume that we have to have either one of them on there. Just because they were mentioned here doesn't mean they have to be on the committee. It could be like this. We could take those 2 people and choose neither of them. In which case, from the remaining 7, we'd have to choose 3 boys. And then from the remaining 5 girls, we have to choose 2 of them. Okay, so there are basically 3 little scenarios here that we have to enter in. And so now, go to the calculator here. And actually I can shorten this up a little bit because the only terms here that are going to give me some interesting information here will be the 7, choose 2 from that first expression, and then the 5, choose 2. And here's my or. Remember, this is one where I chose Jack. Or we don't choose Jack, we choose Jill, in which case from the 7 remaining boys, we got to choose 3. But from the remaining girls, we only need to choose 1. Or, remember, we don't tell them anything. Don't even let them know there's a committee going on. So that's going to be 7, choose 3, times 5, choose 2. So 735 ways we can choose this committee without having both Jack and Jill on the committee together. Now, before we leave this question, I should point out that there is another way that we could have done this one. Another thing that we could have done here was to take all of the possible committees here. Now, again, there's still a restriction here that we have to have 3 boys and 2 girls here. So we had 8 boys to choose from, so 8 choose 3. And we had 6 girls to choose from, and we were choosing 2, so 6 choose 2. So 8 choose 3 times 6 choose 2. This is all of the possible committees that have 2 girls and 3 boys. Because we have this restriction about Jack and Jill here, what we can do here is we can subtract from this total the exact opposite of what we're looking for. Okay, I am looking for committees that do not have both Jack and Jill on it. So let's subtract the number of ways that Jack and Jill are both on the committee. So think of it like this. We've got those two of them there. We're going to choose both of them. Two choose two. Now, if we do that, then there's 7 boys remaining, and I still need to choose 2 boys from that group. And there are 5 girls remaining, and I still need to choose 1 girl from that group to finish this committee. And it turns out, if you do it this way, you still get that 735 because it's exactly the same thing. In this first method, what you're doing is you're kind of building that committee up from scratch, like looking at all the different ways it could be built. Here, we're looking at all the possible committees and subtracting the opposite of that of the thing that we're looking for.
Using a standard deck of cards, answer the following. How many 5-card hands can be formed with at least 1 black card?
Okay, now again, a question like this can be done in a couple of different ways. I think for some of you, the most obvious way to do this is, okay, it has at least 1 black card. Well, now remember that in a deck of cards, you're going to have 26 black, 26 red cards. So you could do it like this. 26, choose. I need to have at least 1 black card, so it could be 26, choose 1. And if you do that, then you need, whoops, whoa, I don't know why my notation got all weird there. Then I'm going to choose 4 red cards, or I could choose 2 black cards and 3 red cards. Or I could choose 3 black cards and 3 black cards and 2 red cards. Or I could choose 4 black cards and 1 red card. Or I could make all 5 of them black and none of them are red. Okay, that's one way to handle this problem. This would also be equivalent to looking at the total number of hands that I could make here, and that's going to be 52, choose 5. And what I'm going to do from that is I'm going to subtract all of the possible ways I could do this. That's the exact opposite I'm looking for. Now, I was looking for at least 1 black card, meaning I could have 1 to 5. Well, the exact opposite of that would be none. So I could subtract from that the situation where I've got no black cards and all red cards. And the result is going to be the same no matter how I set this thing up here. And what I get here is 2,533,180.
How many 5-card hands can be formed with at most 3 red cards?
Okay, here we are looking at a similar question here, except in this case it's at most 3 red cards. Now, at most 3 red cards means what I've got here is I could have no red cards up to 3 here. So it could be no red cards, in which case they're all black. Or I could have 1 red card, in which case I've got 4 black. Or I could have 2 red cards, in which case I had 3 black. Or I could have 3 red cards, in which case I have got 2 black. So that's one way of doing this problem. Or what we could do is take a look at the scenarios here. We'll take a look at all of the different hands, and what we'll do is we'll subtract from it the exact opposite. Now, at the exact opposite of having at most 3 red cards is having more than 3 red cards, meaning you could have 4 red cards, in which case you would have to have 1 black card, or you could have all 5 of them are red and none of them are black. Anyway, in either case here, regardless of how you set that up here, you're going to get 2,144,480 different hands.
How many 5-card hands have 3 kings or 4 kings?
Okay, so in this case right here, again, the key word here is the or. Okay, so I've got 2 different scenarios here, and I'm going to have to deal with both of them and add them together. Now, the first issue here is the kings. So now, again, when we've talked about questions like this before, you got to kind of assume here that you're cheating in essence here, and you're going to think, well, what choices do I have to make to get my partner that I'm cheating with here this particular hand here of 3 kings? Well, there are 4 kings in a deck to choose from. I need to choose 3 of them. So that's going to be 4, choose 3. But once you've chosen that, okay, what's the next remaining choice here? Well, I have to fill in the other cards here. So I've already looked at 4 of those cards and I've chosen 3 of them. So 52 minus 4, 48. Of the remaining 48 cards, I need to choose 2 of them to finish up that hand. So this has got to be 48, choose 2. Or I could have all 4 kings. Now, if you've got all 4 kings, well, that's actually pretty straightforward. And there's only really one way to do that. Okay, you've got 4 kings. You're going to choose all of them here. But what we have to do there is still fill in that remaining card here, and that's going to be 48 cards left over. I need to choose one of them to finish my hand here. And when you press enter on the calculator, after entering that in, you get 4,560 different hands that have 3 or 4 kings in them.